and most of the organizational things. We have a bigger team for the organization of the lecture this year, so we have several tutors, and we have also another person doing introductory material in the next two lecture blocks. That is Johannes Schwert. He will introduce some fundamentals to you guys because we are currently revising our lecture materials a bit. We wanted to do the whole lecture in a different format, but unfortunately we are restricted to this strange conditions again, but I think we will manage to provide you with all necessary material also in this winter term. My name is Andreas Nürnberger. I'm professor for data and knowledge engineering here at the Faculty of Computer Science. In our research we are doing different things, so we are working in a quite interdisciplinary setting in between information retrieval, machine learning and human-computer interaction, building interactive systems for information exploration. There's a question. Okay, we can try. Is the volume now better? Okay for everybody? Everybody can hear me? Okay, perfect. There's some... Okay, should be fine. Okay, danke. Okay, so then I'd like to officially welcome to this year's course on machine learning. Please do not forget to log in to the system, so scan the QR code, or if you prefer not to scan anything or install anything, here's also sheets you can fill and forward at the end to me. However, the digital version is a preferred way to register. The regulations, I have to inform you that you have to wear the mask throughout the lecture. Besides, please observe the seating regulations, so there are marked places where you can sit. I think everybody has picked a place which should fit to these regulations. And that is, I think, everything concerning the current restrictions we have to obey for regulations. Probably I've read it, the registration information you enter into UniNow for the infection tracking in case something like this might be necessary is not used to check your attendance here at class. So it's a separate database, and the information is not distributed anywhere. We don't check any attendance here in the course, that's up to you. We only check if you are actively participating in the exercises. That's actually starting already the requirements we have on the course. So the homepage, I think everybody has found already, I hope at least. It's a long link, but don't worry, you will find it if you look at our main page and look for teaching, and then you find this link. You can also directly go to the Moodle page, but please register at LSF and Moodle because we need this information also for internal purposes to check the amount of people that we have here at class. Lectures given by me, Andreas Nürnberger, and exercises and exams. The main person to contact is Markus, so you know, meanwhile, both of us. Please send, if you have an urgent email request, the email to both of us, or at least make sure that you send it to Markus, because he doesn't receive, maybe I'm actually not sure if it's still the case, not so many emails as me, and sometimes emails drawn in my inbox, so please also, you can remind if you didn't get a response immediately. General information. So what we require from you is basically active participation. And that's part of all university courses, I think, that you don't just consume what we are talking to you, what we are explaining, but especially in the exercise class, we hope that you get more interactively involved. We have exercise sheets with more or less theoretical and practical things. So questions basically in a way for understanding, we call it, and programming assignments. And you have basically to work on both of them. Of course, theory is necessary, as in all courses. Practice is quite important, especially if you are going to work on data science, in the data science area later on, because then you usually have to do really data mining, machine learning in the real world. And if you never have done it using standard technology that is out there these days, you will easily run in trouble and don't really see the issues that are out there. So that's why basically we have a mixture, and also hopefully you will understand the algorithms we are discussing about the machine learning models better if you apply them in practice. Every week is an assignment sheet out there on Moodle. Please download it, work on it, and hand it in. You will upload it to Moodle again, and then it will be discussed in class. We have physical classes and we have online classes. The preference for people who are here in Magdeburg should be to be in the physical class, because it's more interactive. In Zoom we have already always the problem that we see many nice names, but we don't see you. And it's much more interactive if we see your reaction, if we have the impression that you understood what we are talking about, and it makes feedback much easier. So I'm not sure if the online classes are already filled.
I did it just now.
Okay, we will check. Because enrollment is still possible until the first week of November or at some point. So the number of attendees might still increase. That's what we have to take care of in the next few weeks.
There's a question.
Yeah.
The Moodle link is not already on your website that you showed us.
It's not? Then we will update it.
But if you register, so if everybody who registered in LSF correctly, sorry it was so late, it's my mistake. So everybody I could enroll to the Moodle course is already automatically enrolled now. Everybody who I couldn't enroll automatically, please sign in using the key that I sent to you via email. So you've got the key via email at least. Yeah?
I have a question to the exercise class. I'm just in the group which is online because we didn't get place. When we will get the information about Zoom link to participate in the class? Because it's already this week.
So the class does have next week only the exercise.
So not this week. Okay.
So I hope everybody understood the exercise classes start next week. So just in case somebody didn't get the information. More questions? So as I mentioned, please sign into LSF and Moodle, and then we make sure that everybody gets the information you need.
So we just we will get the link back later on this week.
The Zoom?
Or the Zoom meeting exercise.
Yes. So I will put all necessary information on Moodle. That's why it's important that you're all in the Moodle stuff. If you're not yet in the Moodle for some reason, because I couldn't automatically enroll you, or because you were registering very late, because some people registered just before the lecture now, I mean, then I might not have hit you yet, then please tell me, but everybody should have at least the key for enrollment. So just go into this e-learning platform, enroll to this machine learning course. Worst case, you can use the ID here if you don't find it. And now the Zoom link is not on there yet, but I will definitely put it on there this week. Also the exercise sheet I will put on latest tomorrow so that you can solve it. The first exercise sheet is very easy, so don't worry about this. All exercise sheets that come after this will be online at least 1 week before.
This is the key, but actually, so I have to look for the course.
It's not hard though. You will find the best. Sorry, I had to write it quickly before coming here, that's why it's a bit confusing.
Yeah, you can just go to eLearning OVGU.de and you will find it if you navigate through the course list. And it shouldn't be that difficult to find. More questions? Then some remarks to the requirements for the exam. So we will have a written exam at the end of this course, usually in February. Maybe we have to scatter the exam in a longer period because we also need bigger rooms for the exams this year, and so the examination period might be a bit extended, so it might be in March, but the announcement of the exam dates will be most likely in January, and the examination office tries always to make sure that there's no overlap with the exams, but we hope that this is also the case this year. What we expect is, as I mentioned already, active participation in the exercises. That is hard to check, that's up to you, how much you are involved. What we can check is if you submit something, and so we expect that at least half of the achievable points for programming assignments and 2/3 of the achievable points for understanding, so more theory, discussion related assignments have been accumulated by all of you. And what we usually expect, we will see how we can handle this this year, is that everybody presents the solution at least one time in class. Don't worry about it. It's basically required that you present what you have done. So you can, you will be asked by one of the tutors, by Markus or the other people doing the exercises, to present a solution. And it doesn't need to be perfect, so don't worry about it. It should be a training on starting to present a result you have achieved and presenting it. That's what you need later on anyway in different situations in your life, for sure. So that's what we try to train here, that you're actively getting involved into discussion and presentation. If the solution is not perfect, of course the tutors doing the exercise class will correct it so that everybody gets some feedback what would have been the best or at least a good solution for the exercise that you are discussing. On the other hand, by presenting, we also get some feedback from you. What are your difficulties? And then we can support you appropriately. So that's twofold the idea, So to see what maybe is not covered well in the course yet, so we can provide immediate feedback in the exercises, and on the other hand, provide you opportunities to, basically practice yourself to present in a not so big audience. The exercises are 20 to 30 people usually. I think 30 is the upper limit this year, or do we have more? The biggest course, the biggest exercise class?
25.
25. So that's the range we usually try to stay in to keep it interactive. If you only need, some people sometimes depending on their course of study only need to attend a course, so to have a successful pass. And what we require for this is that you at least pass the written exam in the end, so a 4.0 in the German grading system, and then basically you get a certificate that you attended successfully the course Machine Learning. Yeah.
In medical systems engineering, we also consider something like a seminar, and you told in your website that you will connect it to Moodle. Will you have a separate Moodle, or will it be on the machine learning Moodle?
Most likely we will integrate this information, but we are currently discussing about it, how we handle it this year. But everybody who enrolled and who is a medical systems student will get some updated information. And I think there's also an exercise you enrolled in LSF anyway, in addition, no?
Yes, but it's not the exercise that we actually could take.
We will provide you with, most likely this week, at the latest next week, with updated information. You share most of the material with the other students, but there will be additional material for you actually provided. Okay, for those of you who might be worried that they cannot pass or that he or she cannot pass, we will have written exams after each term. So even though you don't pass this term, you will have the chance after summer term to do the exam again. So this will do every 6 months on average. So after each term there will be a written exam on machine learning. So don't worry about this. Yeah, I think, Markus, did I forget something? If there are no more questions, I think there are some seats. If you would like to sit, here are some seats down there. Okay, then we will start with a more general introduction today. This is a more general introduction to machine learning on a more abstract level. What we added to the course is additional material that we will provide you within the next 2 lectures. That is a bit more on fundamentals, theoretical fundamentals to statistical learning, some statistic material, some more theoretical machine learning material, so that you get the necessary fundamentals for the course and to basically have the background information we would expect if we are talking more theoretical things on learning itself, on machine learning models. These 2 blocks will be given by Johannes Schwert. We will also make additional material available online, recorded, you might call it explanation videos, will be uploaded to the Moodle page. The reason why we did this, because in the last terms we we figured out basically, or we were asked by our students that they very often miss the necessary background, the necessary fundamentals on statistics. That's why we introduce these 2 blocks. We will do evaluation of the course approximately in the middle, and then we would be very happy if you can or could provide us with some feedback how this is done, if this really helps, if this should be modified. So we are doing it in this way the first time, but we are optimistic that it helps everybody to get also the fundament if you like to dig deeper into machine learning. This course itself is a more introductory course. We give you the broad spectrum of algorithms, of methods, of ideas, what machine learning is about. And if you like to dig deeper into details later on in different courses, we hope that this provides you with all the necessary fundamentals. That's currently the idea of the course. Let's see if the next 2 blocks provide you with it. I hope everybody had personal motivations to attend here and not just because it's kind of required based on the course study. Machine learning is a pretty broad field. There are communities more driven by the statistical ideas. Some people call it hardcore machine learning, so where you're really developing algorithms, probabilistic learning approaches and things like this. On the other hand, there's an engineering perspective on machine learning, so where you think more about practical problems, and the machine learning algorithms are more driven by engineering ideas. So these derivations work mainly in the distance-based spaces. So if you cluster, for example, if you work with comparing objects, then you have a very intuitive access to the field from the engineering perspective. What we try in this course is basically to have a look at both fields. Statistical approaches, statistical motivations, which is more theoretical, so don't worry if you might get a bit lost during the next 2 blocks, but we will pick back on this material later on. We try to make sure that everybody can follow, and we hope this is really the case, but do not worry. Try to survive the next 2 weeks, and then we will get back to more practical motivations, but link back to the theory throughout the course. That's currently the idea. The engineering perspective is quite practical, so you can see a problem, and I think on almost all blocks you will be able to get back on track by a practical motivation. Yeah? But at the end of the respective blocks in the lecture material, we also provide you with a more theoretical fundamentals of it. That's currently the idea. Why we are doing it? Because you are a pretty mixed group here. So we have digital engineers, we have medical system students, we have computer science students. So it's a pretty broad spectrum of people sitting here, and of course data and knowledge engineers. And they all have different kind of expectations, and we try to fulfill this quite interdisciplinary requirements. So prerequisites is at least some mathematical fundament, so you should be able to read a formula, and ideally you should know what a statistical distribution is and things like this. But as I mentioned, we will get back to the fundament, so you will have at least a quick tour through the fundamental material next week. The goals, at the end you should have a solid foundation on machine learning itself. You should be able to categorize machine learning approaches. So for example, what is supervised, unsupervised learning, you should be aware of some of the models out there, and you should be able to apply it in practice. And if you see a real problem out there that has to do with data, you should know how to make it accessible for some learning methods. And of course, you should know what learning is about in machine learning. Previous courses, we have no strict restrictions here. As I mentioned, a mathematical fundament is the best you can have. Everybody has done some bachelor course, so you know how to study, at least we hope so, and so the remaining things we will see. Maybe a question, are there specific expectations you have here at the course? I'm asking how many data and knowledge engineering students are currently sitting here? Okay. Digital engineering? Oh, wow, the majority. Computer science and medical systems? Okay, thank you. That's a really pretty mixed group this year. Usually we had many more data and knowledge engineering students during the last terms. Let's see, okay, how we can handle this. Attempts to define learning. Machine learning is about machines, okay? So computer systems that do learning. Machine learning is sometimes also put in the area of artificial intelligence, and it's one of the core methods in this field. That's true, but not the only method. There are some quite old, you might say, definitions, but these are definitions done when the field started more or less developing in the 80s, in the 70s. One is from Simon, 1983. Learning is any process that enables a system to achieve a better performance when working on the same or a similar task in the future. This definition is without any discussion, any reference to what learning really is. So how do you learn? How do you store some information in your system? The only thing we refer to is that we can measure something. Yeah? We, for example, think about you have a technical system that rates if this customer, so for example for a bank, if it's a good or a bad customer. And the system learns by supervising or by analyzing how a clerk working in a bank is rating customers. In the end, we decide simply on the performance, so how good did it classify new customers in the end, if it has learned something. You can transfer this idea also to a production system or to a robot doing something, maybe doing the cleaning the outside area, cleaning your room, and then you check the quality of the cleaning process, and if it's improving over time, you say, okay, it has learned something. That's the only criteria we are applying here. So this can be also applied to classes, to teaching, to any other situation. It's a pretty general definition. We just need something to measure performance. Sounds easy. Maybe it's not so easy. We will discuss about it later on again. And the second definition is learning consists of constructing or modifying representations of past experiences. Here we talk about how we store what we have learned. Completely different perspective. One is on performance, measuring, looking like a black box on a system. Second definition, we look into the black box and we are interested in how do we store the information we learn. And here we really have to think about how learning is done, how we learn patterns, how we learn, how we model how a system should interact with the real world. For example, if you develop an agent, a system, a model that plays checkers or chess or whatever, you have then to think about how to encode the baud state. If you program a robot, you have to think about how to encode the whole virtual environment, how to encode sensor information explicitly, and then you have to model how the robot, the agent, should respond to some input. That's the idea of the second definition. Alternatively, we can think about a learning task, so where we provide some problem and the system has to learn the problem. We will get back to this task-oriented learning in a minute. So what could be typical tasks, however, in the real world? So knowledge discovery is one of the further buzzwords that are used in the AI, artificial intelligence or machine learning community. So how can we discover knowledge? Very simple. You can do a physical experiment. You can throw something, a stone, from a from a huge building, and it falls. Physical experiment. What can you learn from it? You can learn to simulate how the stone, how fast it accelerates when it falls down, or what if you don't let it fall, but if you throw it to the side, what is the curve that the stone is doing? Of course, if you know the physics, you can model it. But if you even know the physical model, you still have some parameters to guess. So what is the gravity constant on Earth? You know that there's a dependency on the distance it falls, how the velocity of an object changes. And then this parameter needs to be fine-tuned in order to adapt the model to different environments. And there we have also already one idea of machine learning. Machine learning is about guessing, ideally optimizing parameters of models that describe a problem, a physical problem, a physical scenario. And you can have a very concrete physical model, a formula describing really how this object falls, and then you have one parameter to optimize, the gravitational constant. Maybe somebody should say, well, it's actually not true, you're missing something. Yes, we are missing. What are we missing if we are doing only gravitational constant? Friction, you mean because of the air? Yeah. If it's the difference if you throw a stone or a feather. The feather falls much slower because the air stops the object depending on the type of object you are throwing. The acceleration is not as fast. So actually the model is more complex. If we would have derived the first very simple physical formula that describes it here, S half gravitational constant time t. That's the way an object has passed. If it is falling for the time t, and the gravitational constant is actually what you try to figure out. And that's basically the velocity the object has at a given point in time. It's the second formula. This works if you're working in a vacuum. This maybe gives you already an analogy to machine learning. Well, we're looking for a formula, a model, we call it later a model that we are learning, yeah, to describe something we are observing. The model we are defining provides a pretty strong constraint of what we can learn. With this simple formula we can only define or learn something, how an objects behave in a vacuum. Simplified world. If we only, in addition, would like to consider it's not called the friction, it's called, I'm looking for the English term, that the air basically, air what? Resistance. Air resistance, thank you. It's a bit difficult to understand you with the masks. Yeah, it's not your fault, of course. Thank you. Yeah, air friction. So we need a more complex model with more parameters. Yeah, and this describes the properties of the object itself, of the air you have. How is the air pressure? Maybe it's not just oxygen in the air, it's a mixture of gases. It might be different if you let something drop in a fluid environment. So in water, there's a different behavior. So you need a much more complex model with more parameters you can define. More parameters have to be fixed, so you have to observe more real-world examples in order to learn something. So the tasks get more complex. I need to observe different objects. I cannot throw just a stone, observe how fast it falls, and then I can pretty easily fix the gravitational constant. Works perfect. You measure, you can even make a stopwatch, a simple stopwatch, do this experiment 2 or 3 times, and then you can pretty accurate already guess this formula. If you think about, you have to consider additional properties of the process you are observing and on a general level. You have to measure some properties of the fluid. You have to use different objects that you are throwing, a stone, a feather, and other objects, and you need to think about how you characterize all these objects with parameters, and how you characterize the air or the fluid where this object falls. And so you get a much more complex system. You need more experiments to learn something, and this is already motivating the task of learning in machine learning, collecting data. The more complex the problem is, the more data you have to collect, and think about how you model the world out there. What are the free parameters that you need to fix? And the whole question could be, should I really know the mathematical formula, the physical formula, or actually I'm not really interested in, as a data scientist, I just want to have a model that describes the physical process. And I might not even know these dependencies, so the task gets even more complex, and the machine learning process, the model, has to collect all this information in addition. So knowledge discovery is the idea to learn something. Data mining, which is interpretable, data mining is usually used in a similar setting. Data mining usually refers to analyzing huge databases and find patterns in this data. So very typical task. It was quite popular when huge databases in shops came up. Then information was collected about buying behavior, and of course this is still quite popular these days. If you think about Amazon, there's this recommendation systems to recommend customers have bought this, so most likely you would also like to buy this product and things like this. That's statistics on big data. So you have a large database on one hand, and you try to derive some rules from it in order to recommend something. And these rules might not be mathematical formulas, that might be really interpretable rules. For example, something like clerks with an income greater than 40,000 euros buy especially expensive insurances. Yeah, that's an if-then rule. And we will see later on that such rules can be derived basically by some specific algorithms, for example, a decision tree. In the end, you can learn these rules from big databases. Sometimes you have even more complex tasks than you combine or have textual descriptions. So it gets pretty complex. You have, for example, patient data, so where a medical doctor writes in real, more or less natural language text, the illnesses, how a patient, the status of a patient is, and in addition, you have some measured data like the temperature, blood pressure, and some additional information you have about a patient. And from this pretty mixed information, you might want to derive, is there is a dependency in blood pressure and what the doctor has described in the written text that you can interpret in some way. So maybe you're interested in something like patients with high overweight are 3 times more often resistant against the AV35 adenovirus. Interpretation of big data sets. A virus, a link to the current situation is quite obvious. That's what many people are currently doing out there, to do some statistics on data which is out there. And if you follow the discussions, you might see that the data which is collected right now is pretty incomplete. So the knowledge about the real danger of the virus out there is quite controversial, discussed. Some compare it with a more severe influenza epidemic only from the symptoms. Some think it's much more dangerous. And so what people are currently trying to figure out is analyzing data and try to get an honest situation, let's call it classification, and also deriving according measures that are appropriate for the situation at hand. So be careful if you are working in this field. You might sometimes work on quite important tasks that might have a strong impact on society. So machine learning people or statistical analysis is sometimes done in quite important environments. And I'm not sure if you have followed the first weeks of, for example, just a side remark that is not directly related to machine learning, but to data fusion, data integration. I think most of you have tracked the publications of the Johns Hopkins universities with some statistics on data they have collected. In the beginning, the data was pretty unreliable. What you could extract from the data was long-term tendencies, but not decisions on a weekly, not even talking about a daily basis. The problem was that some health agencies submit their data because it was not, and actually it's questionable if it's really necessary to update the statistics on a daily basis, because the only reliable information is more or less on a weekly average, because people went more often to a doctor before the week and during the week. At the weekend they don't really go, because you suffer a bit and then you say, well, I can go on Monday. So we have a strong bias in statistics on a very often periodic cycle. Think about data analysis in more general. That's really important if you're doing statistics. You have to really consider these effects. And what they didn't consider in the beginning is that different countries have different behaviors of communicating statistics to their central organizations. So there's a very nice example I had also given in my bioinformatics course where there were some statistics. For example, it was by accident on Sweden, because the Swedish government collects the information on a weekly basis. And if you had a look at the Swedish statistics, it was a very smooth curve. It was slowly increasing and then dropping. And what the curve of the Johns Hopkins University was, you had peaks. Peaks sometimes on a weekly basis, sometimes it was slightly delayed. And what you read in the press was sudden increase in infection rates in Sweden. And this was an artifact of data fusion, because the data was not fused correctly. And this holds for a long time, because what the Johns Hopkins University was not doing, it was not correcting the date in the submission. Because they used the date when the information about how many infections were measured to the agency. But this was partly a collection over the last week, over the last 10 days. And they didn't put it on the date when the infection was really detected by a person. So you had basically to do the date correction in order to avoid these peaks in the statistics. This was not done. And this is still not done with many countries. So be careful if you see some statistics on whatever. Always check if the data is appropriately cleaned. And if you have a look at data cleaning cycles, we will also mention it before, the data pre-processing part. If you work maybe later as a data scientist, is really the part that takes most of the time. Really spend the time, check the data carefully if you're doing some statistics on whatever data you have. Make sure that all informations are valid, otherwise you might get very, very unreliable results. Especially if you are getting artifacts, like these peaks on a regular basis. You should really think about, why are there peaks? Might this be an issue of the data I'm having? Do I have to do some changes in my data pre-processing? That doesn't only, is not only the case in case you have medical data or human data, where you often have this weekly, monthly, or even seasonal cycle, but also if you measure machinery data or anything else. There might be sometimes cyclic changes, and sometimes you have to smooth the data, or at least have a model that is able to handle this. Keep this in mind, otherwise you might have some weird results that you provide to a person who asked you for help. Typical machine learning application these days, face recognition, more or less most cameras can do this automatically. So label the person where you take a photo of course smartphones do it. Older examples are here, handwritten recognition, or the BlackBerry started quite early to do some speech to text conversion. And of course spam classification is also quite important field. That's more or less an historical slide. It's describing Alvin, which is driving, I think it was in the 70s, I should add the date, but we get back to this when we are talking about neural network learning. So it's more or less 30 years old that the first experiments with self-driving cars had been done. This was a test they did on an interstate. They drove with 70 miles per hour automatically on the street, which, however, had certain properties. It was nicely separated from the border, so in the image it was clearly visible where the sides of the street are. And how do they do the learning process here? They had a very simple camera, so it was a 30 to 32 sensor array, not more, 960 pixels. And from this very, very artifact, you have many artifacts here on the individual pixels, very poor image. They tried to learn if the car should go to the left or to the right. So the output of the system was basically the car should steer right or left. And the input was this camera, which was mounted here where the mirror is supposed to be and just looking on the street. How did they learn? How did they train? How did they collect training data? Think about this physical experiment of throwing a stone from something, collecting data. What they did is what the Google cars are doing these days, or other cars, they're driving. There's a car driven by a human, and the system logs all information, in this case only what the camera image is, and if a person is steering straight on, to the left or to the right. So a discretized steering wheel position with 30 units. That's all. And then they observed how the person was driving on the street. They collected this information and then they trained something which you later will know it's a neural network, actually a very, very simple one with only 4 hidden units. And with the 30 output units for deriving the steering wheel position. And this was sufficient to drive on this interstate highway, at least on a sunny day. Yeah, there are many problems involved here, in addition. And then the cars get, of course, more and more complex, and you know these days there are cars out there which, if you think about Tesla or others, which more or less can drive easily. However, the steps to this thing, we will discuss about fundamental algorithms, how to achieve this. Other machine learning algorithms, playing chess or game guessing. There had been different games out there, or of course robots is a pretty big field. We had the picture on the left. It's also from the fairgrounds here in Magdeburg. We have the German Open of robot soccer and different activities. Usually every year. Last year we had to cancel this. And this is organized by some people here from different departments, Faculty of Computer Science, Engineering, and Maschinenbau, Mechanical Engineering. And there are also student teams involved and also teams from local schools or schools throughout Germany. I don't want to go into all details about possible applications because I think we more or less talked about it already. Analysis of finance data, astronomical data, they collect a huge amount of data. You can also do analysis on genetic databases, linking it again to PCR tests or something like this. Analysis of text archives, and in the field of information retrieval, I mentioned already, we are actually working in between this field, information retrieval, human-computer interaction, and machine learning. So learning to categorize text, derive what information is relevant for a person at hand, or developing systems that helps people to organize huge information spaces. And also, we are thinking about how to model users, how to learn about user interacting with the real world. How can we derive learning user profiles, learn about users itself. What are related topics? I hope it's clear now, by now. Statistics, you will get some more background, as I mentioned, during the next 2 weeks. Sometimes the statistical machine learning is also, if you do data analysis, data mining tasks, intelligent data analysis, it's just intelligence methods to analyze data. Data mining is more the task which is, includes the whole cycle of pre-processing and other things. Databases are the fundament, content management, document management, visualization, user interface. So it's a pretty broad application area where you find discussions about related topics. Okay, so much to the more general motivation. And now we're having a look at learning in a bit more specific, at least a first more formal definition in the following. There was the motivation to define learning as improving with experience at some task. The formal definition of this could be, okay, I have to think about a task. What task do I like to solve with my machine learning model? How do I measure performance? What is the quality with which I am solving this task? Think for about, you would like to learn how fast the stone falls, how to simulate it. What is your performance measure? How would you measure the quality of a model that predicts the position of a stone that you throw? Any ideas?
You could go by accuracy, so how well the model depicts reality, so how close the calculation of the model is to what actually is happening in real life.
Yeah.
And you could go by actual performance, so how quickly the model can calculate this data.
There we have also already 2 performance measures, or 3, it might be even. So the first was, I'm not sure if everybody got the point, the buzzword, I call it buzzword because it's not defined yet, accuracy was defined. So how accurate the system simulates or describes the position of this stone maybe in time. How concretely can you measure it? You can compute, for example, the distance. Yeah, you measure simply the distance, and the distance to the real position is your error or accuracy in a way, so it might be an inverse error you're computing, and then you measure the process. The other thing which was mentioned was in a way performance in the sense of how long a learning process take, or how fast a system, that could be two things. So how long does a system need to learn to predict something? And on the other hand, if you apply the learned system in practice, it might need some time to predict the position of the stone. It is 2 different things. How long does learning take? So how much training data do we need unless I have a model which works with a given accuracy? And in the real world, it might be also interesting that you need a fast response sometimes. Yeah, if you control a robot, it doesn't help if the system is very, very accurate, almost perfect, but it needs a minute to react. That doesn't help. So you would accept that the system is a bit slower, but with a slightly bigger error, for example, as application in practice. Okay, last thing is experience. What is experience? Yeah, the number of experiments, for example, the number of times we throw a stone could be, for example, experience. But we will have a look at some examples in the following. First example is spam email classification. So if you would like to define or build your own spam classifier that filters out your emails, how can you do it? What is task? What is performance? What is experience? Task is for sure, okay, if a mail gets to my inbox, it should be tagged as spam or not spam, maybe even filtered to another box. So that's classifying. So you classify, you categorize each email, if it is a spam email or if it's a not spam email, at least from your perspective. For some people, a spam email is a product which is of interest for them. For other people, it's spam because you never buy this product. Personalized categorization. Yeah, performance measure. How can you measure performance? It could be the fraction of emails classified as spam correctly. The question is, if I get 90% of my emails are spam emails, and I would do a naive spam classifier which simply classifies all emails as spam, what would the performance be, the accuracy? It has an accuracy of 90%, because 90% of the emails are spam emails, and if all emails are classified as spam, 90% of the emails are classified correctly. If you didn't think about this, that's why I mentioned think about task design. You would think, well, it's a nice spam classifier. 90% of the emails are correctly classified. Great. Sounds like a big number. But actually, most emails traveling out there these days are spam emails, and you need lower numbers. And you wouldn't receive any email anymore. It's probably not that what you would like to have. So you have to think about different measures here, so we will talk about it a bit later. How can you tackle this kind of problem? Yeah, and the other thing is experience. You need pre-classified emails that are spam or not spam. If you have used one of the older spam filters, or these days you have some that you can train, then the system asks you to mark emails as spam, and then it improves over time because it learns. Think about learning definitions. It learns from your feedback. So it gets better over time classifying emails that you personally define as spam and helps you to sort your inbox. Of course, you can apply it to different systems. That's just one example. Other examples in learning are usually or very often games, because games are quite nice. They have certain properties. You can motivate people to play, so you can easily gain some data, and people like to spend time very often on playing games, and so it's also quite good to model, because in this kind of games you have a discrete state space. If you think about playing checkers, you have a board, you can derive properties from the board, you know where a stone is exactly positioned at each state, and then you can use this as training data. So think about you would like to derive an algorithm that plays checkers. What we will do in the following is a derivation of a very simple algorithm, just to give you here some information what you can do. And however, you can think about developing more complex algorithms later on in the class. So the task is play checkers. You can define the task for playing, for example, the white or the red or black stones, and then this is what you like to model. Actually, it's not perfectly defined. What you would like to do is you would like to predict, in order to play, which stone to move to which position. That's the task you like to learn, and you would like to do basically a good move every turn. How you measure performance? Yeah, it gets already challenging. You don't want to ask for each stone you played for somebody, is it a good move or a bad move? That's obviously one thing you could do, but it's pretty hard to get this information from somebody, and it's pretty hard to get a good judgment if this is really a bad or a good move. There might be also not a consistent judgment. There might be situations where one player said it's a good move, the other player, no, it's a very bad move. So it's hard to predict. So what could you do if you don't want to ask or don't have a person that you can ask what is a good or a bad move in order to classify each move you might want to do? Yeah, one idea could actually be, I record all moves of a world tournament that is somewhere taking place, and I only know at the end which of the player won and who lost the game. So I don't have a judgment for individual moves. I only know in the end, with a series of moves a person did, he won the game, he or she, and the other one lost the game. Yeah? And then I can assign, or I expect from a more complex learning task, that the learning system is able to assign the credit, either a positive or a negative credit that is assigned in the end to the whole series, to the individual moves. So basically, it's called the credit assignment problem you might find in literature. That's a problem of deriving which of the moves, it might be many, actually caused that the system in the end failed or succeeded. Another more technical example for this credit assignment problem, for those of you who are coming from maybe engineering domain, but also for the others here in engineering, it's a very typical task to control a pendulum, an inverted pendulum. Think about, you have a cart that you can drive to the left and right. And then there's something mounted on top of the cart, and the cart tries to balance it. So it cannot fall to the side in the simple setup. It's fixed, basically it can only fall to the front and to the back. And then the system should learn what should it do if the inverted pendulum falls to this side. Actually what you can do is you accelerate the car in this direction and then it will move up. If it falls down on this side, you move the car to the other side, and in this way you can balance something. Yeah, and it's a typical task for systems engineers to build a controller for such an inverted pendulum. Why is it challenging? It's an unstable system. At one point it will fall, and you need usually to control it continuously to keep the pendulum in an upright position. How can you map this to a machine learning process? What would be what you're controlling? Basically, you're controlling the acceleration of the cart to the left and right. So basically, you get a positive or negative input to a controller to move this cart with a given acceleration to the left and right side. What is the input? What actually do you observe? Think about the falling stone. So you measure basically the positions after each time. Here you can measure the angle in which the pendulum is currently positioned. Maybe if you measure more information, you can also measure the angular velocity, so how fast this thing is currently going in one or the other direction. That can be the information you measure from the real physical world, and the output, your intelligent system or your machine learning algorithm should figure out in which direction should I move the car and with what speed should I accelerate it in order to keep it in a stable state. This was a quite challenging learning thing, reinforcement learning. We will also discuss about it later in the course a bit. To control such systems automatically. So basically the learning setup was done in the thing, you build a controller that gets the measured information about the angular, and your system can tell, okay, move to the left and right. And the only feedback the system gets in the end if the pendulum is still stable or if it's falling down, unstable condition, and you cannot get back to a stable condition later on. What people have done, this was for machine learning people, at least in a simulated environment, quite easy to handle, not that easy. There are different learning methods out there that can do it. But it's also possible to control or learn to stabilize in double pendulum. And for humans, it's almost impossible to control a double pendulum. Basically, it's a pendulum on top of another pendulum. And you should stabilize it in this position. Then you have to predict what happens actually to the top stick on the other stick if it's falling in this direction, and to make a double pendulum even stable. And in the end, the systems are even able to uplift if basically you can think about a double pendulum hanging down and then moving the cart and uplift it so that's in the end stable. It's a highly physically unstable system, and this you can learn just by observing and just giving the feedback in the end the system is stable or not stable anymore. That's the idea or learning challenges people were talking about in different fields. So now we had quite different things. We have learning from text, spam classification, learning checkers, where we will have a more detailed look in the following, and learning, and I hope it's clear, this pendulum thing is not a discrete system, you get continuous input. Yeah, so you don't have discrete angles. Of course you can discretize the system, but that's not the idea here. You have real valued input that you measure, and real valued output from the system with which you accelerate the car in the end. So that's a different type of learning scenarios with different mathematical properties. Okay, back to the checkers example. Learning data here could be you observe a world tournament, or, and that's actually the experience mentioned on that slide, the performance measure was here actually the number of games won, but this is what you can use as learning data also. That's why I had the D to reinforcement learning. Experience can also, I play against another person, or I can play against myself. It's for humans a bit boring, but some people also do it, play against yourself, and then you see how good moves are. For computer system, you can easily implement one system and let it copy it maybe, however you implement it, and then let it play against itself. And then you observe how the games develop. And in the end, you measure, you take the system that you have learned in the end and let it play against humans, and then we are here back to the performance measure and let it maybe even play in a world tournament. Is it a good idea to play against oneself?
At some point, once you actually started learning the game, you're decently good at it, and I think so. If you just do moves randomly, it's probably not that good of an idea.
So what was basically mentioned, I hope I got your answer correctly. In the beginning, you can easily learn. So basically, you apply the rules and you get a good start, probably. But if you only move randomly, after a while, you learn not very fast, because you have to explore different conditions, and on the other hand, if you learn continuously, you might stuck into a local strategy, because you're always doing moves that you learned that are good again and again. And you don't explore the whole space of moves anymore, usually after a while. So you have this self-enforcing property. You're stuck very often with initially learned good strategies, and you are not varying it anymore. So if you think about, and that's what we try to talk later about, there's something like a state space where you act in. Think about the pendulum, the cart. Basically, you can accelerate the cart in different directions with a given speed. You have an interval where you can get, for example, from -10 to +10. That's the output you can have for the cart. On the other hand, you have as input the state space of the input state space to your system is the angle in which the system is placed. If you have from the beginning a controller which works very good, and the cart is always balanced in an almost upright position and it stays there, the system sees never a state like this or this. So it doesn't know in the end how to react to this states, because it hasn't learned anything about such states. In the inverted pendulum problem, it's quite simple, but think about playing checkers. You might not do certain moves because you think they are stupid. So you don't learn anything about it that in the long term they might be actually quite good. Yeah? Because you didn't see the long-term consequences of your move. You didn't observe this, you simply didn't try. So exploration of the state space during learning is usually quite important, especially if you apply things in the real world later on. For example, systems that drive a real car. You need to observe a quite diverse set of state spaces. Thinking about driving outside and you have a camera, you have quite different lighting conditions. If there's a sun, if it's raining, if there's a reflection of sun on the street, and all these things that are out there in the real world. Think of some accidents that have been where self-driving cars had been. There was this truck crossing the street. It was interpreted in the US, it was an accident where a Tesla car crashed under a big truck because it was never trained for something like a truck crossing the street, and it was a bit higher, the truck, and it looks to the system like a big street sign. So it classified it as a street sign and didn't consider it and crashed under the truck. It's a learning problem. So this was a wrong classification of the situation the system was currently in. And there are many more practical application examples where you can see this. In the past, and it's still in many fields that case, if you would like to let a car drive on the street and it has some automatic mechanism, even for controlling the motor, you had to provide to the agency which was giving the stamp, basically, that you can drive legally on the street, that it's stable under all input conditions. A stability proof. Control engineers should know this, that you prove mathematically stability of a controller. There's been done a lot of work in the past, and these days all these rules are getting relaxed because otherwise we cannot have self-driving system, because it's almost impossible to scan the whole state space of possible inputs to your device. This has certain impact, but on the other hand, for some systems you can still do the proof, but on the other hand you cannot and wouldn't be able to let a car ever drive on the street. Okay, getting back to this checkers example. So the task is playing checkers, and the measurement might be percent of games won in a world tournament. We have discussed about the points below already, what is experience, what exactly should be learned. That's what we have to figure out now. What is our input? What is our output? What do we measure? And how shall we represent it? And what specific algorithms to learn it? So the last three questions we have a look at now. Classified experience. So actually that's what do we learn and how do we model it? So the direct learning would be for each state. What is the state of a game? It's actually the position of the stones. So you have the different amount, the number of amounts of possible state space is, depending on the game, the number of possible positionings of the stones you can do. And this would form the state space. And then you would need, for all possible state space, to know the best move. Does it make sense? Well, if I know it, I don't need to learn anything anymore, because I have all information already. Yeah, if I would know for all state combinations the best move, I have the system I'm looking for. Doesn't make sense. On the other hand, I would never get this information because it's an exponential amount of state space combinations I can get. So it's almost impossible to get all these information. So what we are usually thinking about in the real world is I collect for some states information, and then I have to think about how can I, in a way, interpolate between states of a system. What are similar states? Because if I can figure out what a similar state is, then I might do the same or a similar move for the state I'm currently measuring. So what I'm collecting is sequences of play and results of a large number of games are known. That's what we proposed already. And we discussed also already the last thing, which move had the main influence on the final result of the game credit assignment problem. That's the task actually we are having. A teacher setting is typically, that's what we also already discussed. Here it's more clear described, or more formally described on the slide now. Sometimes we talk about teacher feedback in this setup. So does a teacher exist who can be asked? A teacher, of course, if needs to not to be a technical teacher, but at least a technical profession if it's a technical problem, or a good game player if you like to learn something. And then the question is, can the teacher ask for arbitrary position, and does he know the optimal move for each of these positions? That's like teacher feedback, so then I classify my experience. The problem in the next bullet point, so is the training experience representative, is what we talked already about. Yeah? Did we really cover all state spaces appropriately? Is it sufficient to play against oneself? So we discussed the problem. You very often stuck into good strategies. Is it sufficient to play against one opponent? Well, maybe also not, because he has usually a strategy, and if you play against another, he will have another playing strategy, and you might not know how to handle it, yeah, because he's playing completely different. If you play chess or something, then it even gets more challenging than you know how difficult it might be. The underlying problem is covering the space of all states to learn as much as you can. Okay, what should be learned? We have basically different ways to implement a learning process or define, and that's what we call target function. It's actually the function we would like to learn. In the physical thing, throwing a stone, the target function is actually the physical function describing the behavior of the stone over time, how it falls, how it accelerates. And the target function is the best or the function we would actually learn, but we don't know it. That's the learning problem. So we are looking usually for an approximate solution which is as good as possible, giving the simplification of our problem that we are doing with the model we are currently looking at. Simplification, think about the falling stone problem. If we having a model without air, considering air or fluid influences, then it's a very simplified model of the real world. We can add maybe some simple measure for deriving friction forces or whatever might be there, but this is a more complex model then. Okay, target function for playing checkers. What can we do? We can develop a function, a model that looks at the board and tell us, move this stone to this position. Yeah? And that's what probably everybody would think about in the beginning. That's the solution we would like to have. So basically input is board state, output is move, so which stone to pick and move to which position. So I'm mapping basically the board state to a move, and it's quite useful for direct learning. If I would know what board state is good and which move should I derive from it, and if I would know this combination, it's quite direct, and it's therefore called direct learning, so I know the mapping from the board state to the current move. The problem is I need usually a lot of training data, and it's difficult to do similarities. What are similar moves? How can I map it? How can I really learn here? So especially for game playing, another strategy might be of interest. And it's actually very often called a v-value function that you compute. So you derive actually the quality of a board state. And so you compute a score. So if you look at a checkers board and there's two white stones and 8 black stones on the board in good conditions, you would say, okay, for the black player it's a good score, it's a good condition, and for the white player it's a poor board state. So the score function looks always from one player and evaluates the board state for the player. So the good or a bad board state. So what are we actually thinking about here? So now we are not looking for a direct algorithm that would look at a board and tells you what is the stone you should move to what position. Because this learning problem is a bit complex, I try to have a look at it in a more simplified way and have a look at board states and evaluate board states. Maybe some of you know or think about already what to apply. Okay, I compute the quality rating, and then I can evaluate, and that's actually the idea, all my moves. Because what I can do is I have the board state, and I do a move. I simulate a move. And maybe simulate a move of the opponent afterwards. And then I evaluate the quality of the resulting board state. And this is what I'm doing with all moves I can do. And then I pick the one which has, in the end, after 1, after 2, after 3, after 4, after 5, predictions to the future, the best outcome. And then I'm getting much more flexible. Because suddenly I don't need to figure out always which stone to move, but I use the quality of board states in order to be able to simulate different moves and pick then each time the move I'm interested in. So the learning is now to evaluate the quality of the board state and not anymore to predict the correct move for a board state. And the advantage is I can use this board state evaluation, maybe you realized it, I can look in the future. I can decide to have a short look for just 1, 2 follow-up moves, or I can simulate my whole game for 3, 4, 5, 10 moves to the future. And of course this costs a bit time, but then I can do a better move. So do a prediction and pick the best move I can do. Or maybe I can use this look ahead strategy to optimize my board evaluation function directly. And after I have learned something, I don't need to do this look ahead anymore. And I have all in the model I have learned and can directly apply it. And that's actually the idea of this value iteration algorithms or Q-learning that we will discuss a bit later as part of the course. Simplified model here for today. What could be a possible definition of a target function? Yeah, you can rate the quality of the board state and you can decide it's perfect, it's a very good state for me, the perfect state, or a very bad state. Very bad state would be I lose with the next move. Very good state would be I will win with the next move. So, and then you can say, okay, you put the score in an interval, being it from -100 to 100, -1 to 1, it doesn't really matter. It's just rating the quality of your board state. And for this example, we decide, okay, 100 is a good condition, I will win, or I won already. -100, I lost, and with a board state of 0, it's drawn, no winner, no loser. Yeah, if B is not final state in the game, then we can derive an intermediate board state. I can use reinforcement idea, the board state at the end of the game in order to evaluate the current board state. It's maybe not the best strategy and I can optimize it, but it's something I can do. And maybe I can rate it not by using the, I can decrease the value a bit, and there are many modifications here to learn optimal playing. Okay, this gives the correct value, but it's not operation. How to obtain optimal moves, I already mentioned it, but this is what will be on one of the next slides. So, representation of the target function. How can I represent it? The target function can be implemented as a collection of rules, a neural network, a polynomial function of board features, or whatever is out there. So, target function, recall, it's an evaluation of the board state. We would like to have a method, a model that evaluates the board state. What is the input to the function? The board. And you can figure out if it's the positions of the stones, is it a number of stones, whatever you like to give as input, and then you use this information to rate the quality of the board state. What could be, yeah?
So effectively, does it mean that during the training time we are just exploring and not exploiting?
Exploration and exploitation, this terminology is used in different settings in the genetic algorithm community. It's different strategies to do local or global optimization. Exploration, exploitation is to optimize on a fine subject. I think you mean it on a different thing. What we are doing here is thinking, we are still in the modeling process, thinking about what are features of our system that we can measure and that provides some value to the target function we have in mind.
I'm taking in the perspective from a checkerboard. So let's say object is at a particular position and it has 4 different directions to go. So you can either explore in order to go any of those given X position and see what's the reward that he is getting in return.
That's the next step. That's the application of the target function to decide on the move. What we are talking about now is just evaluating. We simplified the problem, so we are not doing this first this direct learning approach, but we are doing the indirect learning approach, and yes, we are implementing it in a way that we can explore different moves we can do. So that's the idea of exploration.
So shouldn't it be better given the fact that if we have a combination of both exploration and exploitation, as in the learning time itself
Yeah.
very huge for the exploration?
Yeah, for the exploration it might be used huge during the learning. The question is, it can be fast later on if we have a good evaluation function in the end that is fast to apply. Yeah, and the idea could be that you have in the end a neural network. You can whatever type of neural network it might be, or another machine learning model that evaluates based on the features we are now selecting the quality of the baud state. And what we are doing now is not the best, it's a possible strategy. Yeah? It's just some idea. So what are features that can be used to rate the quality of the baud state? And here's just an example list. It can be the number of black and red stones, of course. The more black stones are there, the better the situation is for the black player, and the fewer red stones are there, the better situation for the black player, and vice versa. That's surely a valid thing. And then you can get the number of red kings and black kings. The more kings you have, the better is your situation for the opponent. So very simple ideas here. And then you can have the number of black stones threatened by red and the number of red stones threatened by black. So also this gives you some information. What stones can I possibly lose in the next move if I'm doing this? And you can easily think about putting more features here. But let's start for a moment just with these 6 features and think about what could be a good target function now. We can use these values just as input to a neural network that we will talk about later in the course. But we can already think about with the math everybody knows about a simple target function to evaluate the baud state. What we can do is simply saying, okay, I multiply each of these values with a weight and I add all these values up. And this is probably a reasonable evaluation function for the baud state. Because if I'm a black player, I have a positive weight for the number of black stones. Could be just 1 or 2 times the number of black stones plus and now you need a minus value because your baud state gets worse the more red stones you have. So a positive weight for the features that have a positive impact and negative weight for the features that have a negative impact. And then you can think about, you can directly encode already a reasonable evaluation function, target function for your learning process. But of course you don't want to do it manually. You could put an initial guess here and it would rate. But what you would like to have is a system that learns this function. Yeah? So you don't want to evaluate it explicitly, and you anyway don't know how should you put the respective weight, because is it much more important the number of black kings, so it's 2, 3, 4, 10 times more important than the number of black stones, or how should I put the values there? And this is what your system should learn. This is what is then generalized. Of course it's a simple function. It should just tell you the relation in between features and free parameters of the learning model. So the free parameters of the learning model can now fine-tune in a very simple way the importance of features for the target function. How are they mathematically included in the derivation of an optimal target function in the end. There's a specific thing here, W0, which is something like a bias that is able to shift the value function a bit up and down on a constant level. This can help to have, as we will later discuss, you are actually here in vector space. So you have a 6-dimensional data space you are working in. And you can think about how you can combine, how you can put, for example, if you're doing decisions, move a hyperplane think about you're in 3-dimensional space and you would like to separate good from bad moves. Then you could put a hyperplane in space, for example, here in 3-dimensional space, and the same you can do in n-dimensional space. Just what we will talk about later on. But here for now we have this nice, simple target function. So what is the definition of playing checkers right now? We have a task, we have performance measure, we have experience, and we have a representation of the target function, and we can now start learning. The training example are stored as vectors, so we have the true target function, the learn function, and the training value out there. And basically what we have is basically patterns, rows in a database where we have the amount of stones we have, together with if the game was in the end won or lost. This can be if we have stored data.
Yeah, intuitively, bias is, we want the target function to be unbiased. We want to predict something that should not have bias. And we are adding bias. Is that
the bias, as we will talk about later about bias in more detail, it has a negative assumption sometimes. Here it's just basically a fine-tuning parameters to have an offset value, so to fine-tune the offset, what is a neutral baud state and what not, in order to adapt a bit. Okay, so you have collected this information, and how can we derive now the weights? And what we can do is actually to define an error function. Don't worry, that's what you will talk about during the next 2 blocks in more detail. What we are actually trying to do is our function that we are learning has to predict this plus, minus 100 or 0 depending on the patterns as good as possible. What we can do is we can compare the output of our system to the value we would like to have and add up all the errors. That's what this error function is doing. So the sum of squared errors, because an error should only be positive, that's why we square it, has some additional sides effect. We can do derivations in the end. And there's a method that is called least mean square error optimization algorithm to derive the best weights to make this error as small as possible. We are not going to talk about the math today, but this is what you will talk. Here's a very simple idea. We will get back to this when we are talking about learning neural networks. It's an iterative approach basically to fine-tune the weights. So basically the idea is to say if my output is too big, I slightly increase the values that have a negative sign, because then the value gets smaller, and I decrease values that have a positive sign. Only to a small amount. The weights that are linked to a positive input are decreased, and the weights to a negative input are increased. That's what happens here with this learning rate. And so you iteratively fine-tune the weights, and this sounds a bit weird, but there's a very nice mathematical motivation to do so, and this works pretty well, and this is a very simple training rule applied for neural networks. But I hope the idea is clear, So this iterative fine-tuning of weights is what your learning algorithm, be it as complex as it might be, are in the end doing. That is what this machine learning is about. So what did we do? Our design decisions, we determined the type of training experience. We selected game against self, determined the target function, baud value, we determined the representation of learn function, we picked a simple linear function of 6 features, and then we determined the learning algorithm. It's actually, even though I didn't mention it yet, it's a kind of gradient descent algorithm that we will motivate later on in more detail. That's how you can map a learning problem to this machine learning setup. So the topics we will discuss about it are listed here. I'm not going in detail about it. It's mentioned on the web page already. However, we start with a more general introduction. These are the topics that will be introduced within the next 2 blocks a bit more in detail. So what are different kind of learning? I mentioned already the problem of discrete learning spaces, continuous learning spaces. That is classification, so I try to derive 2 groups for pattern. I think everybody has done some function approximation as part of your previous studies, at least I hope so. It's also usually a standard mathematical approach that you have a function that you put into smoothly into a series of data points. That's what is typically called regression problem. As I mentioned, don't worry, it will be described in more detail later on. And you can distinguish supervised versus unsupervised learning. You had some ideas already. Supervised, I have a teacher who tells me what is the correct output for a given input. So what is the output? That can be also for a regression problem. Unsupervised means I don't know. I have to figure out something here on my own, how this data is linked. There are different variations of this that will be more clearly introduced later on. We mentioned already accuracy to measure how the system learns. What machine learning is sometimes also talking about, how many training examples would we need? What is the complexity of the hypothesis? The hypothesis is actually our target function, in which space we had a hypothesis as a linear combination of input values, now a very simple one in this example. It can be much more complex. You can have a polynomial, you can have a neural network or whatever you have out there. And we didn't even talk about noisy training examples yet. But what is a standard problem of learning? What is noisy? If I have misclassified data, that can be if you have customers that are rated as good as bad. Sometimes a customer is rated accidentally as good, or there are wrong values in my database. It's also noise. In physical systems, noise is obvious, it's a measurement error. In real physical system, no measurement is exact. It's always a slight measurement error involved in technical systems. And if you are developing learning algorithms, you have to consider this. And that's why probabilistic approaches, statistical approaches are quite appropriate. Okay, this is what I wanted to talk about in the introductory block today. We get back or get to more fundamental discussions in the next 2 lectures, as I mentioned. You have the possibility to follow additional readings online. There will be recorded explanations. There will be additional reading made available, so that hopefully after the next 2 lectures, everybody is on the same background, on the same status. And then we continue with step-by-step discussion of different machine learning models, discrete algorithms, continuous algorithms. And that's what we talk about then. Are there any questions? If this is not the case, then I thank you for your attention, and then we see us in 4 weeks. The next 2 blocks, or in 3 weeks, the next 2 blocks are given by Johannes Schwert. Okay, thank you for your attention.